What if I told you that every single thing around us, on a level so small we can't even see it, has its own unique signature, like a one-of-a-kind identifier? That's what we're diving into today, this incredible idea of the molecular fingerprint.
All right, let's kick things off with a little riddle. Picture this. You've got a detective, right, working a crime scene, and then you have a chemist over in a lab. They seem like they're in totally different worlds, don't they? But what's the one thing, the one crucial clue they're both looking for?
That's right, fingerprints. They're both hunting for fingerprints to get to the truth. Now, the detective is looking for the classic kind, the ones left behind at the scene. But the chemist? Well, they're looking for a totally different kind of fingerprint. But believe me, it's every bit as powerful. Okay, so to really get our heads around this whole molecular fingerprint idea, we got to start with the original, right? The human one. Let's just quickly break down what makes those little swirls on our fingerprints such a rock-solid tool for identification.
So what's the big deal with our fingerprints? Why are they the gold standard? Well, it really boils down to three things. First, they are absolutely 100% unique. No two people on Earth have the same ones. Second, they're just insanely complex, packed with all this tiny detail. And because of that, third, they are the ultimate way to prove identity. It's like a stamp that says, yep, this is you and only you.
All right, you got that? Good, because now we're going to take that whole concept and just shrink it down. Way, way down. We're leaping from the world we can see and touch right into the invisible world of molecules.
And that brings us to the big question, the one this is all about. Is it even possible? Could something so tiny, millions of times smaller than your fingertip, really have its own unique personal identifier, just like a fingerprint? The answer is a huge yes, absolutely. Think about it. The water you're drinking, the caffeine in your morning coffee, even the most advanced medicines, every single one of those compounds has its own distinct molecular fingerprint. It's this invisible signature that literally makes it, well, it, and nothing else in the entire universe. Okay, I know what you're thinking. If these fingerprints are invisible, how in the world do scientists actually read them? How do you take something you can't see and turn it into data you can actually use? Well, they use this really clever technique called infrared spectroscopy, or IR for short. And the basic idea is actually pretty straightforward. Imagine you shine a special kind of light, infrared light, through a sample of a molecule. Now, just like a dark t-shirt soaks up more sunlight on a hot day, different molecules absorb this infrared light in their own unique way. So by measuring exactly which bits of light get soaked up, scientists can map out a totally unique pattern for that molecule. Now, here's where it gets really cool. Within that whole pattern of absorbed light, there's one specific zone that is just pure gold. It's this range right here, from 1500 to 500 inverse centimeters. Don't worry about the units, it's just how scientists measure the light's energy. Think of it like finding that one perfect station on the radio dial where the signal is crystal clear. In this exact range, the pattern becomes incredibly messy and complex, and, well, that's where all the magic is. In fact, this area is so important that scientists gave it a name. They call it the fingerprint region. Makes sense, right? Because in this little window of light, the energy makes the molecule bend, stretch, and vibrate in all these super complex ways. It's like its own unique dance. And here's the thing. No two different molecules ever do the exact same dance. And that's why the pattern here is totally unique. Okay, so we've established that molecules have these unique fingerprints and we've got a way to see them. But so what? Why is this a big deal? What can scientists actually do with this information?
Well, it gives them some serious power. Three main things, really. One, they can take a total mystery substance, read its fingerprint, and match it against a giant database to figure out exactly what it is. Two, they can check a substance they think they know to make sure it's pure and hasn't been contaminated. Super important for things like making medicine. And three, and this one is maybe the most amazing, they can tell the difference between molecules that are almost identical.
And this is the perfect example of that. You could have two molecules that are basically twins. They look almost identical. Maybe just one tiny atom is in a slightly different spot. But when you look at their patterns in the fingerprint region, bam, they're totally different. It's the ultimate tiebreaker in chemistry.
And that's really the heart of the matter. This quote says it all. Because every single compound has this one-of-a-kind pattern, the fingerprint region isn't just some cool party trick for scientists. It is an absolutely essential tool. It's how they can identify stuff with complete and total certainty. It really makes you think, doesn't it? We have this key, this method to unlock the true identity of pretty much any compound out there. So, if every single molecule has its own unique story, its own signature just waiting for us to read it, what amazing things are we on the verge of discovering next?